Part 3 of how to improve your bioengineering projects, lessons learned from the City of Calgary Repair and Monitoring Program, is about project design. In this presentation, we'll be covering Repair and Monitoring Program design rating results, bioengineering technique learnings, designing for performance, designing for site conditions, designing for diversity, designing for wildlife, designing for natural processes, and designing with the end goal in mind. Let's begin with the design ratings for the Repair and Monitoring Program. Each site was rated on design, implementation, maintenance, success, and BRQI, with an overall score calculated for each site. The results here reflect the average rating across all sites. The average design rating was 14 out of 18, or 78%, placing it in the good category. This indicates that, generally, design documents like drawings and specifications conveyed the project goals well. However, some sites had lower ratings due to limited design information, issues like erosion or inadequate site-specific design approaches, such as missing toe protection, unnecessary synthetic matting, or discrepancy with the City of Calgary design guidelines on scheduling, stock handling, soil amendments, and road and fencing. We review the documentation for each site to identify the bioengineering techniques used across the city. The 9 techniques assessed are shown here: brush layers, brush mattresses, fascines, live staking, planting, vegetated crib walls, vegetated retaining walls, vegetated riprap, and wattle fences. The sample sizes represent the number of 20-meter long transects evaluated for each technique. We'll go over some of the results from this evaluation over the next several slides. Starting with brush layers. Brush layers consist of dormant live cuttings placed in a trench, layered with soil and with tips protruding. There were 37 transects assessed for brush layers, often used to vegetate hard structures like riprap. This technique was shown to be robust and had shown good establishment, especially in older sites. We recommend using brush layers when excavation into the bank is possible, but then consider adding 1 container plant per meter to create a hedge brush layer. This would improve species diversity beyond just willows or poplars. Brush mattress consists of interlaced live cuttings placed on the riverbank. We assessed 7 transects, finding they performed well with sufficient moisture or irrigation, but struggled in dry or shaded conditions. Failure occurred when cuttings were buried too deeply. Shoot densities range from 17 to 32 stems per square meter, greatly exceeding the target of 5 stems per square meter. Fascines are cigar-shaped bundles of 10 to 20 live cuttings that are 2 to 3 meters long, installed in shallow trenches along contours. Since they don't access deep soil moisture, they should be used on moist, shady, or north-facing sites. We assessed 11 transects with fascines and found that they struggled in dry conditions, so irrigation is recommended. Toe fascines can replace rock for toe protection in low exposure areas, using the design reference shown here, which ensures good contact with native soil and moisture versus the design from Site 2 of the Bioengineering Demonstration and Education Project, where toe fascines are implemented. Live staking involves inserting dormant live cuttings from woody species into the ground, burying 75 to 80% of their length to access soil moisture. It's a simple technique and can require very little equipment and no machinery, and so it is often the technique of choice for volunteering planting efforts. We assessed 21 transects and found survival rates around 70%, but because of spacing, there was low canopy cover. So 45% at year 1, 55% at year 3, and 50% at year 5 age class. To improve success, it's important to follow best practices for cutting handling, installation, and soil preparation. Additionally, higher planting densities in the 0.3 to 0.6 stems per square meter should be considered, as this increases canopy cover. Container plantings using stock sizes like number 1, number 2, and number 5 gallon containers and plugs help control erosion, provide habitat, and improve aesthetics. We assessed 55 transects and found good establishment and survival when done correctly. However, container plantings can be more complex than they seem. The most common issues we observed was planting too shallow. To improve success, it's recommended to train installers to ensure consistent, proper planting techniques. Vegetated crib walls are interlocking timber boxes filled with backfill material and live cuttings. We assessed 10 transects of 15 structures in Calgary and identified several design improvements, including Avoid overlapping crib joints downstream, as this can cause backfill washout due to redirected stream flow. Use double-layered biodegradable coir geogrid for backfill containment, as it lasts longer than erosion control blankets and supports vegetation establishment. Specify high-quality untreated cedar for timber to ensure long-term durability. Use transverse connections at joints to shed water rather than notches that trap water and degrade timber. Choose erosion-resistant backfill materials that support vegetation growth and ensure proper compaction to avoid limiting plant establishment. Vegetative retaining walls resist lateral earth forces, retain earthen masses, and protect against scour. These can include mechanically stabilized earth walls or vertical earth or concrete walls with live cuttings. We assessed 7 transects and found good success where our soil pockets were included for vegetation. However, soil compaction reduced survival and growth on other sites. So special care is needed when planting near concrete or rock, as these retain heat, but deep planting in moist soil zones was successful for the cuttings. Vegetative riprap is stone armoring enhanced with vegetation, typically using pole planting, brush layering, or live staking during construction. We assessed 24 transects and found good success with brush layers, especially when cuttings were planted below the water table so that they had wet toes. Success was lower on sites with low soil moisture. Best practices include filling riprap voids with soil or gravel to support vegetation, improve wildlife passage, and create a more natural look. Some sites use soil and matting around cuttings for protection and to aid establishment. A few bare riprap sites were retrofitted with soil and planted, which will be discussed in the Bioengineering Demonstration and Education Project case study presentation. Wattle fences are simple retaining walls made by weaving live cuttings between stakes to reduce slope length and improve erosion control. They're low in complexity and can be built by volunteers or contractors with minimal experience. The repair and monitoring program assessed 1 wattle fence site, though others have been observed in Calgary, with failures observed at sites like Lindsay Park, Riverdale, and Confederation Park. Key concerns for this technique include durability in dry climates, under flowing water conditions, with high failure rates in sites with low soil moisture or high sun exposure. Caution is advised when using this technique on riverbanks. This table shows the permissible shear stresses for various bioengineering techniques at installation, 1 and 2 years post-construction, and 3 to 4 years post-construction. Shear stress indicates the force a technique can withstand, so higher values mean more durability. These values can be compared with expected shear stress at a site to choose the right technique. As the site ages, shear stress increases due to vegetation growth. Notably, several techniques can withstand shear stresses similar to 300 millimeter riprap, about the size of a beach ball. The rankings Norma presented earlier for each of the bioengineering techniques were partly based on year 1 survival and woody canopy cover data. This chart shows year 1 survival for 7 techniques with a target of 70% from the literature. 4 techniques met the target with brush mattresses at 96% and plantings at 94%. The lowest was vegetated crib wall at 57%. Now adding year 1, year 3, and year 5 age classes canopy cover in green with a target from the literature of 66%. Brush mattresses not only met the survival target, but also exceeded the cover target. Plantings had high survival, but canopy cover didn't meet the target. Vegetated crib wall, despite lower survival, met the cover target in the end. So this highlights that performance targets should include both survival and cover. We recommend using survival targets for the first couple of years to confirm proper installation, then transitioning to cover or density as the main metric, since the goal is full canopy cover by project completion. The most commonly used species for bioengineering in Calgary are balsam poplar, hungry willow, sandbar willow, and red osier dogwood. Year 1 survival was moderate in the range of 62% to 78% for the willow and poplar species, despite their strong rooting abilities. Red osier dogwood had low survival at 49%, which aligns with past observations, and it's been recommended to use container plants or plugs instead of live cuttings for the species for a number of years. Of the 31 species assessed, sandbar willow performed best in year 1 survival, leader growth, and shoot length. It's highly recommended for bioengineering designs because it's native to the Calgary region, has excellent rooting ability, has high tolerance to flooding, high velocity flow, drought, and browsing, and has an ability to spread quickly through suckering. While sandbar willow is highly recommended, biodiversity should still be prioritized in bioengineering designs. The repair and monitoring program data helps identify other species to include. So this table from the final program report shows year 1 survival and year 1, year 3, and year 5 age class growth data for 12 species of live cuttings, providing insights into their growth habits and helps in selecting other species for design. The same data is also available for container plants. Looking at year 1 survival data for different stock types, overall survival for planted woody vegetation was 76%, which is above the typical 70% target. However, there was a significant difference between stock types. Container plants had 94% survival, while live cuttings had 69% survival. Based on this, we recommend using container plants where appropriate, for example, on top of banks in low erosion areas, and live cuttings in high velocity, high erosion areas. To enhance species diversity, we suggest combining container plants with live cuttings in techniques like hedge brush layers, which I've mentioned now a few times. So hedge brush layers are similar to traditional brush layers, but also include rooted plant species, typically at 1 to 2 plants per meter, offering several benefits over traditional methods. Firstly, you can include additional species beyond those that root from cuttings, such as alder, saskatoon, and chokecherry, and those enhance diversity. Species like alder, which fix nitrogen, improve soil fertility, unlike willows, which don't have this benefit. Shrub species in hedge brush layers can produce berries, supporting a broader range of wildlife compared to willows, which provide limited food sources. And finally, including species from the next stage of riparian forest, such as chokecherry, helps transition the site from willows to a more mature forest as willows die off. Some may worry that adding container plants to hedge brush layers could lead to more competition and poorer establishment. However, comparing year 1 survival and growth parameters shows little difference between hedge and traditional brush layers. In fact, hedge brush layers tend to perform better in density and cover, strengthening the case for their use. We documented several recommended practices, including the use of soil amendment and fencing that will be discussed further during the presentation on construction. I've mentioned tall rooted stakes a few times, but they are a hybrid live cuttings and container plant vegetation stock that can be used in the same way as a live stake, but installed outside of the dormancy period, so in July to September. They've been used in at least 4 different bioengineering sites in Calgary that I know of and have established really well in these construction scheduling challenges for summer construction. Key findings from the repair and monitoring program to support successful vegetation design include deep planting. For dry climates, live cuttings should be buried deeply to access soil moisture, especially on hot, dry aspects. This ensures wet toes for the cuttings. With respect to soils, we want to avoid anaerobic or compacted soils as they can cause high mortality. Over 3/4 of the repair and monitoring program sites had significant soil compaction, which impacts plant growth. With respect to installation depth, follow best practices for planting depth, as shallow planting led to high mortality at several sites. A key takeaway from this presentation is to avoid using synthetic materials in bioengineering designs for wildlife considerations. About 30% of the 69 repair and monitoring program sites use synthetic erosion control mats, geogrids, or wattles, where biodegradable alternatives were available. These materials will now persist on riverbanks and in rivers, posing risk to wildlife, as shown in the photo of a garter snake trapped in matting in the top left. The other photos highlight how long plastic materials can remain, more than 12 years on the Bow River, as shown in the photos on the right, and over 34 years in Kananaskis in the bottom left. For these reasons, the use of synthetic materials is strongly discouraged. Now, to incorporate wildlife-friendly techniques into bioengineering designs, in-stream boulders are a good option in the top photo right. They provide excellent fish habitat by improving hydraulic diversity and overhead cover. Rock riprap should be void-filled or covered with native materials to enhance wildlife passage, vegetation establishment, and aesthetics, the bottom left photo. Woody debris supports moisture retention and organic material input when placed on the bank in the bottom right, for example, or provides habitat when placed in stream in the top right. So overhanging vegetation, the lower middle photo, offers shade, cover, and reduces water temperatures, with 2 to 3 meters of cover observed at several sites, which really benefits fish habitat. A key consideration in bioengineering design is how roots interact with structural materials. Once established, roots bind soils and rocks together, providing effective stabilization. The photo at top left shows root growth for a 7-month-old live cutting, and the photo at top right shows the red fibrous roots growing in native gravels, demonstrating how roots stabilize both the immediate area and extend to surrounding soils for water and nutrient access. Roots also grow around rocks and through crevices, regrowing to their original size without displacing the rocks. This highlights that roots don't typically destabilize erosion protection structures, contrary to common engineering concerns. When designing a bioengineering project, it's crucial to design with the end goal in mind, which is 100% canopy cover for optimal erosion control and habitat. While natural collination of bare riprap might seem like a good idea or a solution, it often leads to invasive weeds, as shown in the results from Cavalier and al. On the top right and the RMP in the bottom right. To achieve the desired outcome, plan for vegetating riprap with desired native species and include soil material to support healthy vegetation growth, rather than leaving it bare and allowing invasive species to take over. In summary, the design component of projects observed in the repair monitoring program was typically good, so keep up the good work. Several learnings were identified for the 9 bioengineering techniques assessed under the repair monitoring program, which were presented earlier. Some bioengineering techniques provide shear stress resistance equal to 300 millimeter average diameter riprap. You should measure performance by both woody vegetation survival and cover or density. You should design for species diversity and stock type, and design for deep cuttings to get to available soil moisture. Please avoid using synthetic materials. You should design to facilitate natural processes, and finally, do not leave riprap bare. Void fill or cover it and plant it. The next presentation topic is seeding by Alan Dodd.